Hello everyone, and welcome to GTC Digital. My name is Alex Sabatier. I'm a Global Account Executive at NVIDIA, colleague on strategic retail accounts. In this session, we are going to review why NVIDIA AI SDK powers retail applications. I will start by a description of the state of retail, why AI is designed to help this industry in its current state of transformation, and why it makes so much sense to build AI-based application out of NVIDIA SDKs. Then, Paul Hendricks, who is a brilliant solution architect at NVIDIA, specialized in the retail industries, will dive into the architecture, AI models, and performances of some of the SDK like Intelligent Video Analytics, or IVA, Conversational AI, and data science. We can all agree that the world of retail is in complete disruption, complete transformation. E-commerce, of course, is one of the driving forces of that change. It started 20 years ago and it still grew 5 times faster than the overall retail industry, and now represent more than 10% of the global retail sales. This trend drives a direct impact on the retail industry physical landscape, affecting dramatically stores selling goods easily accessible online, while stores not affected by online sales continue to grow, like gas station convenience stores, liquor stores, pet store, discount store, and so on. And it is not the only change. Customer behavior changed drastically as well, from a linear model where the customer used to go to the goods to a way more complex model where the goods are going to the customers. Connected shoppers now have access to a way larger pool of products and services, access multiple vendors at once. They can check prices, reviews, and order from anywhere at any time. And all that process just happened in a few minutes. This new consumption model drastically impacts supply chain, logistics, pricing, and customer engagement. So the retail world had to adapt and transform to embrace those changes. Of course, technology and innovation plays a central role to create new products and powers those new experiences. Retailers change the way they approach their customers, build personalization systems to make better and even more relevant recommendations. They take into account demographic and societal impact when engaging. In this very competitive landscape, it's important to well identify and leverage existing assets. And you can see that now traditional brick and mortar turn to their network of store to support omni-channel strategy. Buy online and pick up in store or return in store are now widely deployed, used, and appreciated by a lot of customers as it reduces friction. All that transformation has to occur while addressing environmental and financial challenges. In a nutshell, I would say that now the retail industry drives a large set of very complex retail real-time problems, generating and requiring a huge amount of data. And this is why AI is so relevant for the retail industry. I'd like to stop a little bit about how AI drives new solutions. This McKinsey survey claims that the two main areas AI will impact are sales and marketing and supply chain. One directly impacts revenue generation, while the other reduces the operating cost, both impacting the bottom line. There are clear examples where AI reduces friction, like voice ordering, ad tech recommenders. On the other end, data science, driving forecast, asset protection solution powered by compute vision contribute to reduce operating cost. We can all agree that AI in retail has recently started, and it could still be very challenging to deploy for a lot of retailers. McKinsey identified a couple of high AI performers. We have seen their profit multiply by 3 thanks to the use of AI influencing both revenue generation and cost saving. Those AI high performers consider AI their Valerian steel, a very powerful instrument of growth in a competitive environment, and share common practices shown by the survey. They plan a full corporate strategy around AI, have a clear data AI governance, and are committed to increase their investments. Those are the 3 main characteristics that they are sharing. This approach could be very challenging for retailers. With only 2% net profit margin, their investment has to be fruitful almost immediately and carefully plan to limit expenses. Spending too much time to explore use cases and area of interest or value could be extremely dangerous, as the competition may already enjoying the benefits from AI solution and gaining market share. It then makes sense for retailers to reuse, share, and cross-pollinate within their organization when it comes to AI. Reuse infrastructure and hardware deployment, which could be used by various lines of businesses. Creating center of excellence, providing the platforms, the tools, the frameworks to build, evaluate, and deploy AI use cases more efficiently. They also need to stay very closely connected to the AI community, who develop more and more efficient models at a very high pace, and make them available to the whole industry via white paper and large communications. And this is why it makes sense that the NVIDIA stack for retail is extremely relevant. Let me show you why. As you know, NVIDIA GPUs are accessible everywhere, from your preferred cloud service providers, OEMs vendors providing GPU servers, or even NVIDIA DGX, which are AI specialized appliances. On top of those hardware, we develop and enable several layers of middlewares, libraries, and industry-specific frameworks to enable application. The NVIDIA AI software stack for retail is made of 4 main SDKs. Those SDKs use CUDA-X, a middleware acceleration library for data science, graph analytics, deep learning, training, and deep learning inference. There is also a dedicated set of firmware to enable orchestration, deployment, and management using Docker containers, Kubernetes, and Helm for edge deployment. The first SDK, named Metropolis, accelerates intelligent video analytics. With Tensor RT and DEEPSTREAM, it guarantees the highest number of video streams you can run on a specific system and ensure cost-effective deployment. Rapids is a set of open source libraries for data science, powering use cases like forecasting, finance, pricing, anomaly detection, and some type of recommenders. ISAC is our SDK for robotics, of course using computer vision and reinforcement learning to train robots faster and more accurately. Finally, Jarvis is our conversational AI SDK, supporting state-of-the-art models for automatic speech recognition, natural language processing, computer vision, and text-to-speech. Recent models like BERT enable amazing use case when talking to machines. Training, fine-tuning, and inference are fully optimized, providing extremely pleasant experiences. And you will see that Paul later on will come back and dive deeper into those 3 of those 4 SDKs. Now, I want you to understand that those SDKs use the same foundation and allow applications and services to be built on top of it using the latest model, coming from the AI community and fully optimized for GPU. It is easily accessible as containers from our software repository named AGC, which also contain pre-trained models. And so it is widely used by ISVs and retail startups, all included in this family we call Inception, providing solutions for asset protection, autonomous store, demographic analysis, threat detection, and so on. Cloud service providers are also using those frameworks to make them available, or using part of it via their ML machine learning practices, search engines, and NLP voice solutions. Retailers like Walmart or Domino, having their own team of data scientists, are also using those for building and developing their own retail application. As a takeaway, I would like you to remember the following. The AI software stack for retail provides an optimized foundation to build cost-effective solutions using state-of-the-art models and allowing third-party or in-house developed applications to run on similar hardware, whether it is deployed in the store, the data center, or a public cloud. A multitude of use cases use it actually, and we expect way more to come in the near future. Now, let me give the floor to Paul, who will dive deeper on Metropolis, Rapids, and Jarvis. Thank you very much.
Thanks, Alex. Hello, everyone. My name is Paul Hendricks. I'm a senior data scientist with NVIDIA, where I help retailers with their deep learning and AI initiatives. My background is primarily in retail, and I've spent the past 6 years working with a number of well-known retailers on state-of-the-art AI solutions. I've been with NVIDIA for about 2.5 years now, and before joining NVIDIA, I worked as a data scientist at Victoria's Secret building models to understand customer propensity to purchase and how to optimize assortment in store. And today my research focuses on IVA, intelligent video analytics, conversational AI, and machine learning. And in the rest of this session, I'm going to dive deeper into the current state of the art for each one of these different topics and talk about some of the different algorithms and SDKs that are out there. So to begin, let's start with intelligent video analytics. There are many problems in computer vision, the simplest of which is image classification. Usually, data input here are images or videos, and the goal is to identify the class that the input belongs to. And so a common application of image classification in retail is to identify SKUs and products, usually at the self-checkout to prevent loss and theft. Another problem is object detection. Again, here we have inputs such as images or videos, but the goal instead is to identify if one or more objects are in that input. And furthermore, we want to be able to identify the bounding boxes around that object. There may be multiple objects in the image, like in this example below. There's a human, a dog, and a horse. And it's not just good enough that we have bounding boxes around those objects. We want those bounding boxes to be really tightly cropped. And so common use cases of object detection in retail are to identify and track humans and shopping carts or maybe pallets, or even products on a shelf for use cases like inventory monitoring. A last common problem in computer vision is object segmentation, often called semantic segmentation. The goal here is to take some input, often an image or video, and classify each pixel as belonging to a particular class. For example, in the images here, we have children playing soccer. The algorithm can identify each of the children and output a segmentation mask where each pixel in the segmentation mask belongs to a unique class. A common usage of segmentation techniques in retail are to identify SKUs and products on the shelves for inventory monitoring, or even to identify empty shelving itself. Empty shelving correlates to out of stock and can be combined with an up-to-date planogram to create a real-time system for inventory monitoring. All of these techniques and more can be used to solve important use cases in retail, such as preventing loss and theft, better understanding who is coming into your store and how they're interacting with your products, and ultimately solving the holy grail of frictionless checkout, such as that pictured here. This is one of our partners, Standard Cognition. As you can see, the algorithms are able to identify unique individuals within the video, as well as the products that they're interacting with. The algorithms are sophisticated enough where they can even identify which items belong to which people and track those items as they change from one person to another. So we talked a little bit about image classification, object detection, and object segmentation. And in the next couple of slides, we're going to take a little bit of a deeper dive into object detection. So there are several algorithms for doing object detection, the simplest of which is to use a sliding windows method. You slide a window over the image and take that window and pass it to a standard convolutional neural network. This approach tends to work, and you can use pre-trained models like ResNet-50 or MobileNet, models that are trained on open images or ImageNet, for example, to perform the classification. However, using small windows and small strides tends to be very computationally intensive. For example, just imagine striding over an entire image using 1 pixel strides. Additionally, if the window only has half the object in it, the activation may not be strong enough to classify that window correctly. Since convolutions are basically sliding windows, we can try replacing the fully connected layers at the end of our neural network with convolutional layers, resulting in a fully convolutional neural network. If the object is in the image, one of the feature maps in our final layer will activate, and we can identify loosely where the object is. And I say loosely because the bounding boxes that are generated by a fully convolutional neural network are generally not as accurate. Another algorithm called RCNN proposes regions for the neural network to look at. These are a little bit more powerful and are more accurate with the bounding boxes, but also have some downsides that are similar to the sliding windows approach. For example, RCNN generates 2,000 proposals and passes that to the neural network. This is often slower because each one of those proposals has to be evaluated by the convolutional neural network backbone. These are often called two-stage detectors. In contrast, single-stage detectors are a group of algorithms that take the image and output 3 things: the top left coordinate of the bounding box, the bottom right coordinate of the bounding box, and the class of the object in the bounding box for every single object within that image. These algorithms typically are faster because it only looks at the image once. In fact, one of the more popular model architectures out there is called YOLO, which stands for You Only Look Once. Other algorithms that are single-stage detectors are SSD, RetinaNet, and RetinaMask. When thinking about which models to choose for an intelligent video analytics project, it's important to think about some of the trade-offs such as accuracy and latency. Some use cases demand highly accurate models. However, these models tend to be larger and use more GPU memory and tend to have a higher latency, meaning that without optimization, there may be challenges being able to use them in real-time applications with high-definition data at 30 frames per second. Here, we show 2 graphs that show the relationship for accuracy versus latency for several popular models. Models such as YOLO and SSD tend to be fast, but not as accurate, whereas models like FastRCNN or MaskRCNN tend to be really accurate, but not as fast. In general, we recommend working with RetinaNet models for object detection and RetinaMask models for object segmentation. Our essay pursuit engineering team has spent a lot of time optimizing these models, both for training as well as inference, and so these models will be very accurate as well as very performant during inference. Here in the table, we see that a RetinaNet model with a ResNet 152 FPN backbone can outperform many of these models here while still being able to achieve 30 frames per second when optimized with Tensor RT and Int8. There are sometimes challenges with designing and training computer vision models. For example, you need to be familiar with a deep learning framework like PyTorch or TensorFlow. Or if you're leveraging an open source model repository, the model implementations may lack accuracy or may not be optimized for GPU training. Lastly, it's sometimes difficult to migrate a trained neural network model to an optimized format like Tensor RT if the model implementation uses unsupported layers. One of the NVIDIA SDKs that helps developers circumvent these challenges is the Transfer Learning Toolkit. The Transfer Learning Toolkit is a Python-based toolkit that enables developers to take advantage of NVIDIA's pre-trained models and offers capabilities for developers to adapt popular network architectures and backbones to their own data and do things like training, fine-tuning, pruning, and then exporting to something like Tensor RT. It has support for classification and object detection models and provides a very simple path to Tensor RT for deployment. One of the coolest features in the Transfer Learning Toolkit is the ability to prune models. One can train a model, and after a first round of initial training, one can choose to prune the model. Pruning identifies the neurons that aren't contributing to activations and removes them. This significantly reduces model size and has the benefit of improving latency, model memory size, and throughput, all without affecting model accuracy. Here, we saw a 6.5 times decrease in model size and a 2 times improvement in FPS during inference, again without losing any model accuracy. We've mentioned Tensor RT a couple of times, but let's talk about what it actually is. NVIDIA Tensor RT is an SDK for high-performance deep learning inference. Once you've trained a neural network, you'll want to deploy that neural network, often with very time-sensitive requirements. Tensor RT-based applications perform up to 40 times faster than CPU-only platforms during inference. With Tensor RT, you can optimize neural network models trained in all major frameworks such as PyTorch and TensorFlow, as well as calibrate for lower precision with high accuracy, using precision formats like FP16 or int8, and ultimately deploy to both embedded and to data center and cloud platforms. Once the neural network has been optimized using Tensor RT, it's time to deploy. DEEPSTREAM is the SDK of choice for deploying neural network models for intelligent video analytics applications. DEEPSTREAM is a streaming analytics toolkit. It is built on top of GStreamer, which is an open source media framework, and it uses a plug-and-play approach. This allows developers the flexibility of using the plugins that are available, as well as the ability to design custom plugins. DEEPSTREAM can work anywhere, whether it's on-premise in a data center, in the cloud, or even at the edge on a server with T4s, let's say in the back of the store, or even on a Jetson device, embedded, for example, in a mobile robot. This is a typical intelligent video analytics pipeline that's been constructed with DEEPSTREAM plugins, and at the bottom, it shows the underlying hardware that is used by that plugin. The first step is capturing the streaming data coming from the camera. This could be coming from an RTSP stream, from a file, from a USB or CSI camera. After capturing that data, the first step is then to decode the stream. The decoder plugin uses the NVDEC hardware accelerated decode on NVIDIA hardware. This is different from the CUDA cores on the GPU. After decoding the frame, there might be some pre-processing that needs to happen. This could be things like image conversion, image scaling, cropping, or if the stream is possibly from a 360-degree camera, then you might need to do something like de-warp the image. There are various accelerators for these operations. The next operation is inference, which usually performs something like object detection, classification, or even segmentation. After inference, you might need to track the object for insights. And finally, the last step, and sometimes this is optional, is to view the video on the screen with the attached metadata, or even just send that metadata to the cloud for further analytics. There is quite a bit that is new in DEEPSTREAM 4.0. For example, you'll find that the SDK is more unified and that writing code across all platforms, whether it's on Tesla or on Jetson, is a lot easier. We also have turnkey integration with IoT cloud stacks, the most notable of which is the Microsoft Azure IoT stack. And there continues to be great support for Docker containers, which are available on NGC. There's also now support for working with raw image input formats like monochrome or JPEG, as well as support for image segmentation techniques like UNet and maskRCNN. There's also now greater support for plugin services like passing messages. And lastly, we've come out with Python bindings for DEEPSTREAM, and we're working to make developing applications even easier with even less code. Now let's talk a little bit about conversational AI, a new and really exciting development within the field of AI. So what is conversational AI? When people think about conversational AI, they sometimes think about Amazon Alexa or Google Home or Siri. And these are excellent examples of conversational AI agents. However, a lot of the interactions with these AI agents tends to be transactional, as opposed to conversational. You might ask questions like, what time is it? Or where is the nearest Thai restaurant? But ultimately, these conversations lack nuance and context, and as a result, don't have the depth and tone of conversation. For example, if I said I really like the sushi place you recommended last week, a conversational AI agent might ask what I liked about that restaurant, register that information, and then recommend on the spot or in the future other restaurants or venues that align with those stated preferences. A transactional AI agent would fail to overcome this hurdle. In this example, a conversational AI agent is able to use nuance and context to improve the interactive experience and facilitate better recommendations. Another important element to conversational AI agents is the need for real-time response, usually on the order of a couple hundreds of milliseconds. Conversations happen in real time, and it's not good enough for me to say something and then Amazon Alexa to respond to it 30 seconds from now when I've already forgotten what I've asked. Lastly, these models need to be very large. The human language is incredibly complex and oftentimes involves several steps of language modeling and understanding to capture the hierarchy of our thought paradigms. These large models complicate the need for real-time responses, and GPUs greatly reduce this burden by accelerating the ASR, NLP, and TTS models significantly. And we'll talk more about what those are. And in the same way we're seeing how GPUs are transforming conversational AI, we will see speech transform every industry. Specifically in retail, we will see conversational AI used for shopping online, as well as for shopping in brick and mortar. Imagine being within a home goods department store and interacting with a conversational kiosk to find the right size screw for your home project. Or ordering a pizza or going to a drive-thru and placing a fast food order. Other use cases involve internal uses of conversational AI, such as upskilling employees and being able to answer questions on documented procedures and protocols. Conversational AI will allow us to scale the retail workforce. The race to conversational AI over the past couple of years has been fascinating to observe, and it's been interesting to observe this within the context of GLUE. GLUE stands for General Language Understanding Evaluation and is a benchmark for general natural language processing and understanding tasks. There are human-level baselines for this benchmark, most notably at scores of 87.1 and 88.8. Over the past couple of years, models such as MTDNN from Microsoft, AccelNet, Alice, and BERT variants have surpassed these human baselines. Today, these models are capable of superhuman performance in natural language understanding tasks. One of the key reasons why these models have been able to surpass human performance has been the ability to create and train larger models. As I mentioned, the human language is very complex and difficult even for native speakers to understand, let alone in AI. Having larger models allows the ability to go beyond now seemingly simplistic tasks like recognizing images to doing things like question and answering, sentiment analysis, and translating from one language to another. With the success of these initial NLP models comes larger models that can solve tougher use cases like chatbots, email autocompletion, document summarization, and even generate coherent paragraphs of text that seem like a human wrote them. These models, like GPT-2, 8 billion, for example, are 300 times larger than a traditional ResNet 50 model, with new larger models coming out every couple of months, like Microsoft's 17 billion parameter model, which is a whopping 600 times larger than ResNet 50. NLP models are just one piece of conversational AI. When we think about the general workflow, there are a couple tasks where a deep learning model can be used for each task. In general, a conversational AI workflow might look like the one pictured here. A user interacts with some application by stating a question. In this example, let's say, what is the best Greek restaurant nearby? The application will capture the audio in an audio file, and this audio file is passed to an automatic speech recognition model, often called an ASR model, that then converts the audio into text. Wave to Letter and Jaspar are two ASR models that are capable of converting audio to text. Next, the text is passed to one or more NLP models like BERT. Query, understanding, and formulation tasks are performed here, and sometimes those results are passed to search or even recommendation tasks, each of which usually employ even more neural networks. Once the response to the user has been formulated, it is passed to a text-to-speech, sometimes called a TTS model, like Tacotron 2. The speech is then sometimes passed to a voice encoder model to make the sound more natural and aesthetic. As you can imagine, each of these neural networks are quite complex. And as we mentioned, it's very important that this be real-time with responses back to the user in less than a second. On a traditional CPU, this whole workflow might take 14 seconds, which is well outside of an acceptable range. On a GPU, though, it takes about 500 milliseconds or half a second, which is well within acceptable range. There are a couple popular models out there for doing ASR or automatic speech recognition, and two of the more popular ones are called Jaspar and QuartzNet. Jaspar takes as input some audio file, splits it into 20 millisecond windows with 10 millisecond overlaps among the windows, and calculates audio signal specific features. The architecture of Jaspar is block-based, where a typical model is said to be of type Jaspar B by R, where B is the number of blocks, and each block has R subblocks. Each subblock, depicted here, has a dropout, ReLU, batch normalization, and Unde convolutional operation, and each block input is directly connected directly into the last subblock via a residual connection. The subblock architecture of Jaspar was designed to facilitate fast GPU inference. Each subblock can be fused into a single GPU kernel, where dropout is not used at inference time and is eliminated. Batch normalization can be fused with the preceding convolution. ReLU will clamp the result, and the residual summations can be treated as a modified bias term in this fused operation. QuartzNet is another ASR model that is more recent. I won't go too deep into it, but QuartzNet is very similar to Jaspar. However, instead of using purely based convolutions, QuartzNet uses one-dimensional time channel separable convolutions, which has a couple of advantages. It's faster to train, requires less computation and memory, and has a higher inference throughput. Once we have our input converted from an audio format into a textual representation, we can start to work with it to process it and understand it. This is sometimes a multi-step process and can even feed into other steps such as search and recommendation. One of the most common models for doing natural language understanding is BERT, which stands for bidirectional encoder representations from transformers. There's a couple parts to dissect here. The first part is the transformer part. Transformers are a concept that use self-attention and essentially compare a segment of words against itself. In this way, language is learned contextually, as the underlying representation of a word in a language is learned using other words around it. The next important part is the bidirectional part of BERT. In historical neural networks, typically RNNs and CNNs, sentences were usually read from left to right and their context and meaning inferred in a one-directional manner. However, English and language are rarely that simple. For example, words that come later in a sentence can sometimes affect or have a relationship with words previous in the sentence. For example, in the sentence, "The big black bear is silly," we might modify our understanding of bear with big and black, words that precede the word bear, as well as with the concept of silliness, a word that follows bear. Using a bidirectional approach allows us to capture these nuances in language and structure. The last piece of a BERT model is the encoder. An encoder is the part of the model that translates or encodes some data into another representation. Here, we mean that BERT encodes our raw textual input into a lower-level representation, often called a latent space, where this latent space captures the patterns and relationships between words. We can use this lower-level latent space as input into subsequent models for doing classification, recommendation, or even search. After we're done with our natural language processing and formulate a response back to the user, it's time to convert that textual query back to an audio representation. The most common way to do this is to use the Tacotron2 and WaveGlow model. The Tacotron2 model will convert the text to audio, and the WaveGlow model will convert the audio from one voice representation into another, often one that is smoother, more pleasant, and more natural sounding. So let's say that we have a particular workflow in mind, and we'd like to compose a series of neural networks, train, and deploy them. How would we go about doing this? The two key toolkits out there for doing such a thing are NeMo and Jarvis. NeMo, which stands for Neural Modules, is a toolkit for defining and building conversational AI applications. Neural modules are conceptual blocks of neural networks that take typed inputs and produce typed outputs. Such modules typically represent data layers, encoders, decoders, language models, automatic speech recognition models, loss functions, or methods for combining activations. The toolkit comes with an extendable collections of pre-built modules for automatic speech recognition, ASR, natural language processing, NLP, and text synthesis, text-to-speech, often abbreviated TTS. Once these neural networks have been defined and trained, it's time to deploy. NVIDIA Jarvis is an SDK for building and deploying AI applications that can fuse vision, speech, and other sensors. It offers a complete workflow to define, train, and deploy GPU-accelerated AI systems that can use visual cues such as gestures and gaze along with speech in context. So now that we've talked a bit about computer vision and conversational AI, let's talk about machine learning. Many data scientists and machine learning engineers are familiar with the open source data science ecosystem, which is composed of software like Pandas, scikit-learn, NetworkX, and more. These are the tools that data scientists reach for first when starting a project. These are all fantastic tools, but we've seen that as data size increases, these tools, which are CPU-based, tend to be slow. And data scientists spend more time waiting for results than they do spend actually doing meaningful analysis and work. To solve that problem, we've created Rapids, which is an end-to-end ecosystem for doing accelerated data science. We've built on top of the ideas of Pandas, scikit-learn, and NetworkX, so the APIs are identical or nearly the same. However, the underlying operations and algorithms have been GPU accelerated, so data scientists are able to accomplish the same work often 10 to 100 times faster than their CPU equivalents. So let's dive a bit deeper into each of their packages. The main package for doing ETL is called cuDF, which is short for CUDA data frames. This is the GPU analog to Pandas and is great for manipulating tabular-like data structures, often called data frames. The interface for cuDF is in Python, and you'll find very little difference between Pandas and cuDF, which is great because you don't have to learn a whole new syntax. Instead, you can focus on getting your work done quickly and enjoying the benefits of GPU acceleration. cuDF is a lot faster than Pandas, too. Here, we show some benchmarks comparing cuDF from version 0.10 to Pandas 0.24.2. Here, we show a plot comparing the GPU speedup over CPU for a couple of common ETL operations like merges, sorts, and group bys. And we show the speedup for a dataset that has 10 million rows in purple and a dataset that has 100 million rows in light blue. And as you can see, as our dataset size increases, so does the GPU speedup. But even with a small dataset of 10 million rows, we still see anywhere from 28 to 430 times speedup. And with a larger dataset of 100 million rows, we see speedups from 150 to 870 times over CPU. These operations were done just once, and often in ETL, these operations are done many times within a single workflow. So the more times these common operations appear in your code, the more benefit cumulatively you'll see from using cuDF and GPUs. As I mentioned, this plot shows cuDF 0.10, and we're currently on cuDF 0.13. So as you can imagine, things get faster with every update. Similar to how we have a GPU analog for Pandas called cuDF, we have a GPU analog for scikit-learn called cuML, which is short for CUDA machine learning. Almost all of the algorithms that are available in scikit-learn are available in QML with support for decision trees and random forests, linear regression, logistic regression, things like XGBoost, clustering algorithms like k-means, dbScan, and spectral clustering, decomposition and dimensionality reduction techniques like UMAP, principal components analysis, and TSNE, time series algorithms like Holt-Winters, ARIMA, and Kalman filtering, and many more algorithms. You'll also find the API for QML to be very similar, if not identical, to scikit-learn. Consider this example where we create an artificial dataset of 2 clusters and then fit a clustering algorithm to the data. The makeMoons function here creates a dataset of 2 half-moons where each half-moon has a different centroid, as pictured here on the right. The x variable here is the raw data, and the y variable are the true labels on which point belongs to which half-moon. And both x and y variables are NumPy arrays. We can then convert the NumPy arrays to a Pandas data frame and instantiate a dbScan model from scikit-learn, fit the model to the data, and generate predictions for which cluster each data point belongs to. Here, we show the exact same process, but instead we use QDF and QML. As you can see, the only difference are the import statements. Similar to how QDF is faster than Pandas, QML is faster than scikit-learn. Here we show the GPU speedup over CPU for several of the algorithms for different datasets. In general, we see more GPU speedup over CPU with larger datasets. For example, with 4 million rows, we see speedups of almost 70 times to 6 times. Even with smaller datasets of 1 million rows, we see speedups of 64 times to 4 times, which is really awesome stuff. And now that we've introduced rapids, we can think about the current data science ecosystem as a graph with 2 axes, where the y-axis is the ability to accelerate or scale up, and the x-axis is the ability to scale out or parallelize. On the bottom left-hand side of this graph, we have the current open source PyData ecosystem that runs on CPU and is composed of NumPy, Pandas, and scikit-learn. And as our data gets bigger, we can scale up and accelerate our algorithms using rapids and the GPU, which is composed of QDF, QML, and QGraph. As our datasets get even larger, we can scale out and parallelize using tools like Dask and OpenUCX, which makes it possible to scale to multiple nodes, where each node might have multiple GPUs. And to date, most of our roadmap has focused on making sure there are a variety of algorithms that have been accelerated on a single GPU. However, we recognize that real-world datasets are larger, often too large to fit in a single GPU's 32 gigabytes of memory. And our focus on 0.13 and beyond is building functionality to make it easy to build and train machine learning models on datasets that are hundreds of gigabytes in size or even terabytes, and to be able to write clear and concise code that is GPU accelerated and fast, while still easily scalable across multiple nodes. To conclude, there are a lot of really exciting things happening in retail with a large focus on computer vision, conversational AI, and machine learning. And we saw the critical role that NVIDIA GPUs and SDKs play in these areas. We hope you've enjoyed our presentation. Thank you for watching.